this section, we are going to discuss the Dining Philosopher Problem. It's a very exciting problem, an interesting problem that gives us some idea of how to approach a synchronization issue. Here we have 5 philosophers sitting around a dining table. As any philosopher does, they will think for a long time, and when they feel hungry, they're going to start eating. So the table has plates of food in front of each of them, and there are 5 chopsticks. And these philosophers, when they eat, they need to use both the chopsticks. So when a philosopher wants to eat, the protocol that he will follow is he will try picking up the chopsticks nearby. For example, the philosopher D0 will try to pick up C0 and C1. That is, he'll try to pick up the left one first and the right one. D1 will pick up the chopstick C1 and C2 and so on. If the philosopher has picked up the left chopstick and he does not have the right chopstick free, he is going to wait. Or if the philosopher does not have any of them free, he is going to wait. If the philosopher gets both, for example, if D0 has got C0 and C1 both, he will start eating, and once he finishes eating, he will put down the chopstick. Now this is a classic case of concurrency control. How do we allocate several resources to processes without causing deadlock and starvation? As this particular definition of the problem can actually lead to deadlocks and really starvation, because the philosopher may not get to eat anything with one particular algorithm. So we need to find solutions where we can avoid the deadlock and the starvation. So let us look at one of the solutions here. So we're going to use an array of semaphores called chopsticks with 5 elements, and each of them initialized to 1, which means that each element is a binary semaphore. So one semaphore indicates the availability of a chopstick. So we allocate one semaphore for each chopstick. The algorithm to be followed by the philosopher is fairly simple. He will look at each philosopher will look at the chopstick that is left to him, which is indicated by I, and the chopstick right to him, which is indicated by chopstick I plus 1 mod 5. For example, D0 will look at chopstick C0, that is DI will look at CI and CI plus 1, which is D0 will look at C0 and C1, and D1 will look at C1 and C2, and D2 will look at chopsticks C2 and C3, and D3 will look at chopstick C3 and C4. And D4 will look at C4 and C0, which is I plus 1 mod 5. So this goes on. So essentially, each philosopher will look at 2 chopsticks, the left and the right. When he gets them, he is going to use them, finish up eating, and then release both of them. So this looks a good solution until we have a condition where each of the philosopher has thought enough and they want to start eating at the same time. Now they're going to get into this particular loop at the same time. Each of them will pick up the chopstick on the left. D0 is going to pick up C0, D1 is going to pick up C1, D2 picks up C2, and finally D4 picks up C4. So D0 wants to eat, but he has only C0 in hand. He cannot use C1 because it's occupied by D1. And the same thing happens for the philosopher D1. He is taken up C1, but is waiting for C2, which is taken up by philosopher D2, and it goes on. So each of them is actually waiting for the other's release. As we have seen, this is a case of a deadlock and starvation as well, because everybody is actually going to really starve in the true sense of the word. So how do we avoid this? We can look at a simple method where we allow only maximum 4 philosophers. We leave the number of chopsticks to be at 5, which is C0, C1, C2, C3 and C4, but we have one space in the table empty. So we allow, for example, here, as per the same algorithm, D0 will take C0, but he's going to wait for C1. D1 takes C1, waits for C2, and D2 has taken C2 and waits for C3. D3 has taken C3, but he's got C4 also available, so he's gotten both, and he starts eating now. So here we got D0, D1 and D2 waiting, but D3 is actually eating. If the wait is indefinite, we have a deadlock situation. But in this case, let's see how it proceeds. So here we said D3 has taken both the chopsticks. So he's free to eat now. He is going to eat, and he will complete his dinner, and then he's going to place back C3 and C4. When he does that, C3 becomes free. Who's waiting for C3? It's D2, because D2 has C2 in his hand. He's waiting for C3. Now D2 can start eating. So C2 takes some time to eat, and finally D2 takes some time to eat, and he's going to place back the chopsticks. So then who's waiting for C2? It is D1, because D1 has already taken this particular chopstick. He is waiting for the chopstick on his right, which is C2. Now when this is available, he is going to start eating. He completes his dinner, and finally D0 has his dinner in the same way. So in this particular situation, we have avoided deadlock and starvation. However, this goes in the order of D3 going first, then D2, then D1 and D0. Only one person is eating at this time in this particular method. So let us look at method 2. Here the philosopher will pick up the chopstick only when both are available. That is, only when left and right are available. He is not going to take the left first and wait for the right, which gets us into the situation of deadlock and starvation. Here he will initially look at whether they are available. Anybody using it. Only if nobody is using it, he will actually take it. So for that, we're going to use an array called available. So that would actually store the status of whether the particular chopstick is available. For example, so we're going to have it from, in this particular case, it's from available 0 through 4. So first, and this particular thing this particular variable access has to be controlled through a mutex, so that it is accessed in a controlled way. So we take the mutex, take the mutex and check whether the availability of chopstick left and then the right, which is indicated by I plus 1 mod 5, is true. If that is true, we make it false and release the mutex. And once we make the available as false, now we go pick up the chopstick. We say that the philosopher takes the chopstick left and the chopstick right. So then he starts eating. Then after he completes eating, he's going to place back the chopsticks and make the chopsticks available, which is indicated by available I is true, and then available I plus 1 mod 5 is true, which is indicating the chopstick on the right. So the access to the variable available is controlled through signal. So this method again avoids the deadlock and the starvation. The third method is fairly simple. It's an asymmetric solution where the odd numbered philosophers, we have got philosophers 0, 1, 2, 3 and 4. So the odd numbered philosophers are 1 and 3. They will pick up the left chopstick first and the right chopstick next. And the even numbered philosophers are 0, 2 and 4, and they'll pick up the right chopstick first and the left chopstick. Now, how this particular method avoids the deadlock and the starvation, we leave it as an exercise to the participants. You have to go ahead and look at how to code this and ensures that this particular method doesn't lead to starvation or deadlocks. Thank you.